Well, welcome everybody to this lecture on complex hyperbolicity. So I will start right now. So as you have maybe already seen, this will be part of twofold lectures with Lionel Larondeau. So I will present to you the general notion of complex hyperbolicity in this video. But before doing that, I would like maybe to recall what is maybe one of the main problems in complex geometry, namely the classification of complex varieties. So suppose you are given a complex projective smooth variety X, and we would like to understand if there are some classes in which we could put our variety X, some natural classes dividing all the complex projective varieties. So there is one situation where this is very well understood. It's in the case of curves. So if we assume that X is of dimension 1, then we know that there is an invariant, namely the genus, which is an integer, and which allows us to put our variety into one of three classes. And each of these different classes has very different properties. So, for example, the universal cover of the genus 0 curves is just P1, and actually in that case X is itself isomorphic to P1. For the genus 1 curves, well, we know that they are complex tori, their universal cover is C. And finally, for the genus higher than 2 curves, well, we know that their universal cover is the unit disk that will be denoted by delta in this whole lecture. Also, there is a different notion that we can study on complex varieties. They are the metrics we can put on them with constant curvature. So, in the case of genus 0 curves, well, we know that we can put a metric with positive constant curvature. In the case of genus 1 curves, this metric will be with a 0 curvature, and in the last case, we'll have a metric with negative curvature, and that's why we call curves with genus higher than 2 hyperbolic. Okay, so these are very geometric notions. And now there is one additional notion that we can study in the case of curves, namely an arithmetic one. If you assume that our curve X is defined over a number field, we can ask ourselves how many rational points there are inside X. So we know the answer, at least when K is a large enough number field, so we know that in the case of genus 0 it will be infinite. The Mordell-Weiss theorem tells us that it will be infinite, at least again if K is large enough in the case of genus 1. And by Folting's theorem, we know that there will be only a finite number of rational points if the curve is hyperbolic. Okay, and before going to higher dimensions, there is one last thing I wanted to say concerning the canonical line bundle of the curve, which is, in this case of dimension 1, none other than the cotangent bundle omega x. And in that case, we know that it will be anti-ample if the genus is 0, trivial in the case of genus 1, and ample in the last case. And you can remember these properties, which are very important and are the basics of what will come when we try to extend this description to the higher dimensional case. Since, as in the case of curves, the positivity property of the canonical line bundle will govern a large part of the geometry of the manifold in higher dimensions. And so let me recall that the canonical bundle of X is just the determinant of the cotangent bundle. And if we are given this object, we can form an invariant associated to any smooth projective varieties, which is its Kodaira dimension. So the Kodaira dimension is an element which is either an integer between 0 and the dimension of X, or minus infinity. And it's the element such that if you compute the plurigenera of your manifold X, so the dimension of the sections of the powers of the canonical bundle, well, you have bound like that, bound from below and from above by a polynomial with degree the Kodaira dimension, at least when n is divisible enough. And we say that X is of general type if this Cadorel dimension is equal to the dimension of X, so if it's maximal. So if you recall what we have said before, in the case of curves, you can easily compute the Cadorel dimension for smooth projective curves. So it's minus infinity in the case of P1, in the case of genus 0. It will be 0 in the case of genus 1 curves, and it will be 1 for genus higher than 2. So the last case is the case of projective curves of general type. Okay, and so if you compute the Cadorel dimension of a higher dimensional variety, you maybe would like to relate geometric properties of X, such as the curvature of natural metrics you could put on them, or the number of arithmetic points you could have on your manifold. You maybe would like to relate them to the Cadorel dimension. But it's actually a very hard problem. And what I would like to explain now is a sort of alternative way to try to relate arithmetic properties, for example, of varieties and the proper algebro-geometric properties of their canonical bundle. So it's a different way which is related to Campana's theory of orbifolds. So that's I'm going to explain now. And let me just say that the goal that we will follow is to relate the classifications of complex varieties to the properties of the entire curves you can put on them. So let me explain what an entire curve is. So it's simply, if you are given a complex manifold, a non-constant holomorphic map from C to your variety. And so in the case of dimension 1, it's easy to study if there are entire curves in a given projective curve, of a given genus. So for example, in the case of genus 0, we know that X, your manifold of genus 0, is P1. So you can find many entire curves inside P1. And similarly, in the case of genus 1 projective curve, you can also find many entire curves on it, since its universal cover will be C. But in the last case, you will not find any entire curve on genus higher than 2 projective curve. And why is that? Well, it comes simply from the fact that the universal cover of X in that case is the unit disk. So if you assume you are given a projective curve of genus higher than 2 and a map from C to your manifold, then you can lift this map to the universal cover by the universal property of the universal cover, and you get a map from C to the unit disk, which is holomorphic but also bounded, since delta is a bound domain inside C. So F tilde is holomorphic and bounded, so it will be constant by Liouville's theorem. And you get that F is constant, so F is not an entire curve according to this definition. So you see here that you have a dichotomy between the projective curves which admit entire curves and the one which don't. And that's this dichotomy that is expected somehow to hold in higher dimensions. So before going to the details, I would like to say that we expect that projective manifolds which are of general type don't admit too many entire curves, and conversely there is a class of manifolds which will be called the manifolds of special type, on which we expect to find many entire curves. So I will explain now what we call a manifold of special type, and as I said before, it comes from the theory of Campana's orbifolds. So let me briefly recall that an orbifold, in the sense of Campana, is a pair where X is a projective smooth manifold and delta is a Q divisor with a simple normal crossing support and coefficient between 0 and 1, like that. And we say so that an orbifold first is of general type if its canonical orbifold line bundle, that is the sum of kx plus delta as a Q divisor, has maximal growth when you compute the sections of its powers. So you have bounds like that, and actually I was a little bit too general maybe in writing these inequalities. You maybe know that if you have inequalities like that, then kx plus delta will be what we call big, and then this h0 here is actually equivalent to such a polynomial, and not just bounded from below or from above. But it's not really important for what we have to say. And opposed to orbifolds of special type, of general type, sorry, we have a notion of orbifolds of special type. So I will just state it for manifolds here. So morally, we say that a projective manifold is of special type if it doesn't admit any fibration above an orbifold of general type. So I will not be able to give you the full details of the definition, but maybe just let me state it anyway. So we say that a projective manifold is of special type if for any fibration above a base B, which satisfies some technical assumption which allows us to call this fibration neat. So it satisfies some additional condition to avoid some degeneracy problem in this vibration. And now if you are given such an object, you can put an orbifold structure on the base coming from the fibration. So it comes from Campana's theory. And so we say that if we are given such a fibration such that the base is of general type, then X is special implies that B must be a point. So it does not admit any non-trivial fibration above a base of general type if you put these technical assumptions on the fibration. And one very important theorem which was proved by Campana is that you can decompose in some way any projective manifold, or more generally orbifold, into orbifolds of special or general type. So what is this precise statement? So assume you are given a complex projective manifold, then the theorem tells us that there is a fibration which is called the core fibration, such that, well, first the base, if you put the natural orbifold structure on it, will be of general type, and the generic fibers of C will be of special type. So you have this sort of decomposition, as I said above, and let me just say also that this core fibration satisfies a universal property, so the fibration of general type under X will factorize through C. Okay, so now you can decompose any manifold into orbifold of special and general type, and if you remember what we said about entire curves, there are two conjectures which I'm about to introduce which relate the properties of orbifold of special type and general type with entire curves. So we expect that these two kinds of objects have very different properties with respect to these entire curves. So let me be more precise. So the first conjecture in complex hyperbolicity is the conjecture of Green-Griffith length. So it tells us that if you have a complex projective manifold, then it should be equivalent that X is of general type, and that there exists a closed algebraic subset, so which we call the exceptional locus, which contains every entire curve drawn on X, and also if X is defined over a number field, then the complement of this exceptional subset should contain only finitely many rational points over your number field. And this should be true for any number field over which you could define X. And conversely, we expect that special varieties satisfy opposite properties. So let me be more specific. Let X be a complex projective manifold, then we expect that there is an equivalence between the fact that X is of special type, or the fact that there exists an entire curve on X which is dense, either for Zariski or Euclidean topology. And finally, that if you assume first that X is defined over some number field, then if you take a sufficiently large number field over which X is defined, then there is a Zariski density of the rational points inside X. Okay, now if you recall the case of curves, well, you can see easily that the two conjectures which I have written before are true in dimension 1, in the projective case. So, if I recall what we said before, in the case of compact curves, then you can see easily that the two cases genus equal to 0 and genus equal to 1 form the special type case, and the case of general type, well, as we said before, is the case where the genus is higher than 2. And then we have Zariski density of the images of entire curves in the first case, and there are no entire curves in the second case. And for rational points, as I said before, it suffices if you assume that your curve is defined over a number field. It suffices, as I said, to take a large enough number field to have density of rational points, so that's what I mean by potentially dense. And there are only finitely many rational points in the case of hyperbolic curves. And so, if I recall what we said about the conjectures of Green, Griffith, Lang, and Campana, well, I can write the following table. So we expect that we have potentially Zariski density of special type of rational points in the special type case, and non-Zariski density in the case of general type, and for the case of entire curves, well, we have the same thing. And so in the following, we will concentrate on this part of the table, namely trying to find restrictions on the images of entire curves inside varieties of general type. And so that's what we call hyperbolicity in a broad sense. We will say that a variety is hyperbolic if there are not too many entire curves on it, and that's what I will try to explain in the following. So, what is the plan of what I will explain now? Well, first I will tell you precisely what we mean by complex hyperbolicity, and morally it's the fact that a given manifold doesn't admit too many entire curves. And now I will explain after that different techniques to prove that a given manifold is complex hyperbolic. Oh, sorry, there is a typo here. I meant how to prove that a manifold is complex hyperbolic. And so I will give you metric methods, and also I will explain, maybe in some details, some jet differential techniques that were very useful in the last year to prove strong complex hyperbolicity results about, for example, hypersurfaces in PN, complete intersections, and many other cases. Okay, so let me start by giving you precisely a definition of complex hyperbolicity. So there are different notions that we can give. So one of the most basic of them is the notion of Brody hyperbolicity. So we say that a complex manifold is hyperbolic in the sense of Brody, or Brody hyperbolic, if there is no entire curve on X, so no non-constant holomorphic map from C to X. And a little bit more relaxed definition is that X is Brody hyperbolic, modulo sublocus, if any entire curve lands in Z. So the Green-Griffith-Lang conjecture, if you recall it, tells you that a complex manifold should be of general type if and only if it is Brody hyperbolic modulo an algebraic subset. Okay, so these definitions are maybe a little bit too coarse for a precise study of complex manifolds and precise study of hyperbolicity properties of complex manifolds, and that's why we have Kobayashi has introduced a definition which permits us to be more qualitative in the study of complex hyperbolicity. So this definition is I am about to explain, introduces a pseudo-distance on any complex manifold, and first to do it we have to introduce an infinitesimal version of it. So this infinitesimal version of Kobayashi pseudo-distance will be a map which goes from the tangent bundle of a given complex manifold and returns a real number. So take a vector which is based at some point small x, and you return the following number, the following quantity. So it will be the infimum over the infimum of 1 over lambda, where lambda runs over any positive real number such that there exists a curve, so a map from the disk to x, such that this disk is based at x, at small x, your point here, and such that the image of the standard tangent vector at 0 is lambda times v. So here lambda, I recall that it's a positive real number. So if I draw a picture, morally this tells you that kx of v should be small if there are large disks directed by your vector v. So if there is such a large disk, you can take lambda here, large, and this will give you a small quantity here. But if there is no such large disk, then kx of v will be rather large. Okay, and the Kobayashi pseudo-distance is the pseudo-distance, well, that you get integrating this infinitesimal version. So how do you do that? So take 2 points over your variety x, and you define the pseudo-distance between p and q by taking the infimum over all paths going from p to q. So you take c1 piecewise c1 path from p to q, and over them you integrate kx applied to the 1,0 part of the derivative of gamma. So gamma prime of t, here it's a real vector, a real tangent vector to x, so that's why you have to take the 1,0 part to get a complex tangent vector, and then applying kx you get your quantity from before. So as I said, this quantity here will be small if there are large disks directed by gamma prime of t. So if along all path, if along some path leading from p to q there are large disks tangent to the vectors along gamma, then this distance will have a tendency to be small. And since it's a pseudo distance, it could happen that it does not separate points, and we say that x is Kobayashi hyperbolic if it's not the case. So we say that x is Kobayashi hyperbolic if the x is a distance, which means that it separates points. So morally it's a distance if there are not too many large disks inside x, so that this quantity is not too small. And if you want to relate this notion of Kobayashi hyperbolicity to what I have told before about Brody hyperbolicity, well, you have the following proposition that if x is Kobayashi hyperbolic, then it will be Brody hyperbolic. So how can you do that? So if you assume that x is not Brody hyperbolic, then there will be an entire curve in it. And I say that the image of any entire curve is the union of arbitrarily large disks. Simply take the image of the disks of radius r centered at 0 inside C and let r go to infinity. And this proved that kx applied to tangent vectors to your image f of c will be 0. So if you integrate a path inside f of c, you will get 0. If you integrate kx along a path inside f of c, you will get 0. And so 2 points of this image are not separated by the distance, the Kobayashi pseudo-distance. And that's why, in that case, if x is not Brody hyperbolic, then x is not Kobayashi hyperbolic. So we have now two notions of complex hyperbolicity and one implication towards the other, from one of them towards the other. And what I would like to say now is that Kobayashi hyperbolicity is strictly stronger than Brody hyperbolicity. So why is that? It's easy to find examples of complex manifolds such that the converse is false. So take, for example, x equal to this manifold. So we take all the points inside the product of the disk and C with this inequality. The absolute value of x times y is strictly smaller than 1, and you remove some part of the y-axis. So I have drawn the picture here. I have removed the part in red to the variety in blue, which is this. And I say that x is broadly hyperbolic. So why? If you take a curve inside x, and map from C to x, and now you want to prove that it is constant, so how can you do that? First, you can project it towards the first coordinate. So it falls inside the disk, so it is bounded. So it's a holomorphic map which is bounded on C. So again, by Liouville's theorem, you get that this projection is constant. And so F falls inside a fiber of the first projection. But from this definition, you see easily that any fiber of the first projection is bounded. So again, apply Liouville's theorem and get that F is constant. So there are no non-constant holomorphic map from C to your manifold X, and X is broadly hyperbolic. However, X is not Kobayashi hyperbolic, since, as I will explain now, if you define P and Q to be the following 2 points on the y-axis, we can see that the Kobayashi pseudo-distance between them is 0. So how can you do that? We will define 2 sequences of points going towards P and Q respectively. So here are these sequences. So you put the same y coordinate for Pn and P, and similarly for Qn and Q, and you take for x coordinate 1 over n. And these 2 sequences are points inside some disk, delta n, which is given here. And as n goes to infinity, Pn tends towards P, Qn tends towards Q, and this delta n here becomes increasingly large. And now you can bound from above the Kobayashi pseudo-distance between P and Q as follows. So you simply use the triangular inequality. It's not too hard to see that this pseudo-distance tends to 0, since Pn tends to P, and similarly for Qn. But what's interesting now is that this pseudo-distance will also tend to 0, since, as I said before, Pn and Qn are points inside a large disk which becomes increasingly large. So that's what I'm drawing here on the picture. So as n goes to infinity, the pseudo-distance between Pn and Qn becomes smaller and smaller. And so at the end, this distance is equal to 0. Okay, so as I have just said that Kobayashi hyperbolicity and Brody hyperbolicity are not equivalent in general, but there is a very important result that they are actually equivalent in the compact case. So my counterexample from before is not compact, and that's why the following theorem does not apply. So this is a theorem which was proved by Brody. X is a compact complex manifold, then X is Brody hyperbolic if and only if it is Kobayashi hyperbolic. And the proof relies on the following lemma, which is Brody's reparametrization lemma, which tells you the following. So assume that you have put an Hermitian structure on your manifold, so you have a metric here, omega, which is Hermitian, and you take a holomorphic map from delta to x. Now take small number epsilon, and this lemma tells you that there is a way to reparameterize delta in the following manner. So first you take a radius, which is almost larger than the norm of f, the norm of the tangent vector of f at 0, almost being controlled by this epsilon. And there is a reparametrizing map from the disk of radius r to the disk of radius 1 minus epsilon, such that the norm of the tangent vector at the reparametrization, so you compose f with psi and it gives you a new map starting from this disk, while the norm of its tangent vector at 0 is just 1. And for any other point, the norm is bounded by the Poincaré metric. Okay, so we will now explain how to prove this lemma. So don't hesitate to pause the video at some points. Normally in my slide I have given all the details. So first, there is one thing we will do is to replace the first map f of t by this reparametrized version. So it allows you to assume that f prime is bounded, since it permits to restrict f to a compact disk inside the unit disk. And we can now replace epsilon by 0. So as I said, since now we assume that f prime is bounded, we will have a bound on the norm of the differential of the the norm of the differential starting from the tangent space to the disk towards the tangent space to x. So you put first on the disk the Poincaré metric, and on x you put your Hermitian metric you have chosen before. And it's not hard to see that this norm is expressed as follows. And as I said, since we assume that f prime is bounded everywhere and even to the boundary of delta, this is also bounded everywhere and it tends to 0 towards the boundary. So we can pick t0 inside the interior of the domain of the disk, where this quantity is maximal. And this t0 will be the new origin of our reparametrization of the disk. So now we pick an R, so it will be large enough at the end of the proof, but for now I will not give you the condition we need on it. And we take a reparametrized map from this disk of radius R towards the disk of radius 1. And we send 0 to t0. Okay, so it's not hard to see by the properties of the Poincaré metric that the norm of the derivative of psi in the Poincaré metric is just 1 over R. And now we can express the Poincaré metric, well, the norm of the derivative of our reparametrized version of f in the Poincaré metric at the origin and the Hermitian metric at the target. And by our choice of t0, we have an upper bound now by this quantity, but at 0 instead of t0 before. And we can now compute on the both left-hand side and right-hand side. We can replace this expression by computing this norm. So you get this expression. It's very similar to this computation here. And it's bounded from above by the norm of the differential of f in the Poincaré metric on this disk and omega at the target, and we multiply it by 1 over R, which is the norm of the derivative of psi for the Poincaré metric. And now you can pick R such that the right hand side is bounded by 1, is actually equal to 1. And it's not hard to see also that you have an equality when t is equal to 0. So as I said, you take R such that the right hand side is equal to 1. So this is the quantity you have to take. And by our choice of t0, this quantity is higher than this quantity when t is equal to 0. And now you can check that all you wanted to prove is true. In the Alford-Schwarz lemma, you have this quantity which is bounded from above by 1. So you have this quantity which is bounded by the Poincaré metric. And the equality at t equal to 0 tells you that this is equal to 1 at t equal to 0. Okay, so now we can prove Brody's theorem, namely that Kobayashi hyperbolicity is equivalent to Brody hyperbolicity in the case of compact manifold. So take X a compact complex manifold, then I claim that X is Brody hyperbolic if and only if it's Kobayashi hyperbolic. So we'll prove that if X is Brody hyperbolic, then it is Kobayashi hyperbolic. So fix a Hermitian metric on X and assume that X is not Kobayashi hyperbolic. We want to prove that it's not Brody hyperbolic. So if X is not Kobayashi hyperbolic, it's not hard to see that you can find a sequence of tangent vectors of norm 1 with respect to the Hermitian metric you have chosen, and such that kx of Vn tends to 0. And if it were not true, you would be able to bound from below kx by the Hermitian metric, and integrating you would see that the Kobayashi pseudo-distance would separate points, which would contradict our assumption. Okay, and now if you recall the definition of kx, this point 2 here is equivalent to the existence of holomorphic maps starting from the disk and going to x, such that the derivative of Gn at 0 has a norm which tends to infinity. And now you can reparameterize all these holomorphic maps, you reparameterize all the Gns, so you find radius radii Rn, which are almost larger than this quantity, so you can assume that they go to infinity. And your reparameterized version of the Gn are maps which start from the disk of radius Rn and go to x, such that you have first at 0 the norm of these derivatives are 1, and at any other point the norm of these derivatives are bounded by the Poincaré metric on the disk of radius Rn. And now you find holomorphic maps with bounded differential, and you can apply Hausdorff-Haskoli's theorem to find that the Fn converge uniformly on compact subset inside these disks, and since the Rn go to infinity, well, you find at the end a holomorphic map on the whole plane C going to x, and you have, if you pass to the limit in these two inequalities, in this equality and this inequality, you find that the norm of the derivative at 0 of f is equal to 1, and the norm outside is bounded by 1 everywhere. So the first point tells you that f is not constant, so it's an entire curve, and you get that x is not Brody hyperbolic. And just let me tell you that for future reference, that a curve which satisfies this is called a Brody curve. Okay, so now we have proved that there are two notions of hyperbolicity which are equivalent, and what I would like to do now for the rest of this lecture is to give you different methods to show that a manifold is hyperbolic in both of those sets. So the first methods I would like to present are metric, of a metric nature, and they are based on a very important lemma, the Alford-Schwarz lemma. So before stating this lemma, I will just recall one definition, namely the holomorphic sectional curvature of a Hermitian metric. So take a Hermitian metric omega on the manifold X. The holomorphic sectional curvature of omega in the direction of a tangent vector. Well, I wrote here, I would like to say instead in the direction of V. Well, it's simply the sectional curvature in the Riemannian sense of omega in the plane, the real 2 plane that you get by taking the real part and the imaginary part of. And now the Alford-Schwarz lemma tells you that if you have a Hermitian metric on the disk of radius r, which has holomorphic sectional curvature bounded from above by a negative constant r minus a, then we have a way to bound from above the norm of tangent vectors to the disk by the Poincaré metric as follows. So you have a constant here, and if you look at this formula, it tells you in particular that the radius r is bounded from above by this quantity. And as a consequence, there is no metric on the whole plane satisfying that satisfying the same inequality as here. So simply, if you had such a metric on C, then you would be able to contradict the Alford-Schwarz lemma by taking a sufficiently large disk based at the origin inside C. And now, if you have a complex manifold with a Hermitian metric with holomorphic sectional curvature bounded from above by a negative constant minus a, the first part of the corollary implies rather easily that there are no entire curves inside X. So X will be broadly hyperbolic. And to prove using the first point that the second point holds, we use the fact that the holomorphic sectional curvature decreases by pullbacks. So if you have a map from C to X, you would be able to pull back to C any such Hermitian metric and contradict the first point if you had an entire curve on X. Okay, so I will not give you the proof of this lemma now. I will just briefly give you some examples of application without giving you too many details. So a theorem, which we can prove using this Alford-Schwarz lemma, is a theorem which is applied to families of Calabi-Yau manifolds. So if you assume that X supports a family of polarized Calabi-Yau manifolds, then a theorem of Griffith and Schmidt will have as a consequence that if this family has maximal variations everywhere, so I will not give you the full details of what it means, then X is broadly hyperbolic. So the idea of the proof is to use this family to produce a metric with holomorphic sectional curvature on X, which is bounded from above by a negative constant. So how do you do that? Well, you use your family and the theory of variation of host structures to produce a period map going from the universal cover of X towards a period domain, parameterizing some well-suited variation of host structure on X associated to your family of manifolds. And now you can see by the theory of variations of host structures that on such a period domain you have a non-positive definite Hermitian form with some curvature properties, and the consequence of some computations by Griffith and Schmidt is that you can pull back this Hermitian form towards X tilde and get a Hermitian metric with holomorphic sectional curvature which is bounded from above by a negative constant. And so the assumption of maximal variations, I can say that it means simply that psi here is immersive. Okay, and so I will maybe stop here this slide about applications. I will just give you briefly some other results which were proved in the very recent years. So the Alford-Schwarz lemma can be applied in the same spirit as this theorem to varieties supporting certain families of varieties other than polarized Calabi-Yau manifolds, or also certain variations of host structures, also to varieties which are expressed as quotients of bounded symmetric domains, since these varieties admit naturally metrics with a holomorphic sectional curvature which is bounded from above. And so many people have worked on these problems, Griffith, Schmidt, as explained above, Vivek, Suo, Johan Brindbar, Biadeng, and myself, and many other people I have not the time to quote here. Okay, and very briefly I will show you the proof of the Alford-Schwarz lemma, but I will be quite fast on it, so don't hesitate to pause to get all the details. So first, to prove the Alford-Schwarz lemma, we expressed precisely that what it means that omega has holomorphic sectional curvature bounded from above by minus a, and you can see by the theory of curvature on disks that it means that you have this inequality. This Laplacian is bounded from below by this quantity. And now you take a point inside the disk of radius r such that this quantity here is maximal. So since it is maximal, if you compute the Laplacian of its logarithm, you get something which is non-positive. And now you use this inequality here to bound from above a times the norm of the norm squared of the tangent vector at t0. So you use this here to bound it from above by this Laplacian, and if you compute this Laplacian, you get actually the Poincaré metric. So now you are almost done. You see that you have this inequality, and you recall that you have chosen t0 such that this is maximal. So you can now bound from above this quantity everywhere by 4 above a times r squared, and if you pass that to the right, you get your inequality. Okay, so you can pause this slide if you want to check the computations. I think the only thing you would like to check is this equality here. Okay, so let me stop here for the metric methods. I will now introduce another kind of technique which is very useful to study complex hyperbolicity. Namely, it's the notion of jet differential equations. So what are they? So consider a complex manifold, and we will fix two integers, k and m, which will be respectively the order of the differential equations we will consider and the degree of these equations. So I will introduce now what we call the Green-Griffith jet bundle of order k and degree m. So it's a vector bundle above x whose sections corresponds to such jet differential equations. So if you take an open subset inside x with some coordinates, then the sections of this vector bundle above you will be the differential equations of order k and degree m, and let me be more specific. If you take a curve inside U, starting from the disk, then P can be expressed and can be applied to F to give you a holomorphic map on the disk, which is expressed as follows. So you take the derivative of the coordinates of F, and you take all these derivatives up to order k, and you form monomials using these derivatives. You can multiply these monomials by holomorphic functions on U composed with F, and you take the sum of these monomials, and you get a polynomial expression in the derivatives of the coordinates of F. So here the order k appears here. It's the maximal order to which you derivate your function F. And where does m appear? It's in the choice of the indexes here. You make this sum run over the L's such that you have this equality. So let me just tell you that it is precisely the equality you need, so that if you reparameterize your map F by multiplying the variable by lambda, then applying P to it will give you lambda to the power m times the former expression. Okay, so I will now give you an example in the case of order 1. So in that case, it's rather easy to see that the jet differential equations of order 1 and degree m identify with the symmetric powers of the cotangent bundle. And to have this identification, you just need to replace the fi prime here with dz I, so where the zi are the coordinates on your open chart, and you check that if you change your coordinates, these two vector bundles will vary in the same way. Okay, and now why do we care about jet differential equations in the study of complex hyperbolicity? Well, it comes from this very important theorem, which we call the fundamental vanishing theorem, which is due to Xiu, Young, and Demailly. So it tells you the following. Assume that you have a complex projective manifold and an ample line bundle of it. Then, if you take a holomorphic differential equation of degree m and order k that vanishes along A, then for any entire curve drawn on X, well, this entire curve satisfies the differential equation. So P of f is equal to 0. Let me just tell you, before giving you an idea of the proof of this theorem, that it is very important here that we have this minus a. Because if you remove it, it will not hold. For example, in the case of an elliptic curve, you can form the following differential equation. Just take dz. So it's order 1 degree 1 differential equation on your elliptic curve. And then if you take the standard quotient map from C to X, the value of this differential equation applied to f will be f prime, and its constant equal to 1. So it's certainly not 0. So hopefully it will appear in the sketch of the proof of this theorem I'm about to give you why we need this minus a. So proving this theorem would need some tools which I don't have the time to introduce here, so I will just give you a simplified proof in the case where we are studying a Brody curve. So let me just recall what a Brody curve here is. So fix a Hermitian metric on X, and we will assume that the curve we are studying is such that for any point inside C, the norm of the tangent vector to f at t is bounded by 1, and we will also assume, even though it's not strictly necessary, that the norm at 0 is equal to 1. So under these assumptions, we say that f is a Brody curve. And so now we can prove the theorem in this case. So first we will cover X by a finite number of coordinate charts, and we will remark that in each of these charts, since we have an upper bound on the norm of the derivative of f, you can apply Cauchy inequalities to give an upper bound above for all the derivatives. So all the derivatives are bounded on each of the inverse images of the coordinate charts. And so if you recall, P of f is a polynomial expression in all those derivatives, so it will likewise be bounded above each of these inverse images, and since there are finitely many, then you get a bounded holomorphic function on C. And so it is, by Liouville's theorem again, constant. So now you know that it is constant, and you want to prove that it is 0, and that's where we will use the ample line bundle A. So the first thing we want to do is to replace it by a very ample line bundle. So how do we do that? Well, remark that if you replace P by sufficiently high power, it will not affect the vanishing of P. And also, if you replace P by such a power, it has the effect of replacing A by the multiple dA, which you can assume is very important. And also, you can prove easily that if you move A in its linear equivalence class, it will also not affect the vanishing of P. And now we can move it and assume that the intersection of the image of the curve and of this divisor is not empty. So now, since PF vanishes along A, well, it will vanish at some point of C, but you knew that it was constant, so it actually proves that it is 0. So this gives you the proof in the case of a Brody curve, and if you want to remove this hypothesis, you will need some Nevan linear theory to do that. But the spirit of the proof is not very far from what I have explained here. Okay, so I will just mention briefly some applications of this fundamental vanishing theorem and refer to Lionel Darrondeau's talk for more details. So there is one very important case where this theorem has led to very important, very strong developments recently. It's the case of hypersurfaces in PN. And so in that case, a lot of work has been devoted to finding differential equations on a hypersurface. So you have a hypersurface and you want to produce sections of these vector bundles. Holomorphic differential equations vanishing along some ample line bundle. And so Simone Di Verio, Erwan Rousseau, Lionel Darrondeau, Joël Mercœur, Jean-Pierre Demailly, Damien Broadbeck, and many other people have worked on this problem. and it has given recently very strong hyperbolicity results. So one of the first results I would like to mention is the following one by Differential, that if you have a hypersurface which is generic and sufficiently high degree, then it will satisfy the conclusion of the Green-Griffith-Lang conjecture on hyperbolic curves. Entire curves. So it will prove that there is an algebraic subset inside X which contains the images of any entire curve drawn X. And even better, since 2015, we have many people who have proved that these hypersurfaces, if they are of sufficiently high degree, they will actually be hyperbolic, and not only broadly hyperbolic modulo sublocus. And so this answers the conjecture by Kobayashi, and there is one result that Lionel will probably talk to you about in his talk. It's a result by Riddle and Young, who have proved in a very nice paper recently that actually the first work by Diverio-Merkel-Rousseau imply in a very nice manner that the Kobayashi conjecture is true. And finally, I will just tell you that these holomorphic differential equations, they are only one part of a larger picture which was developed to study also non-compact varieties. So, for example, you have a logarithmic equivalent to these jet differentials, which was developed by Noguchi and also Tetlow-Flew for different versions of these jet differentials in the spirit of work of Jean-Pierre Demailly. And also there is a Norbifold version of jet differential which was recently introduced by Campana-Darondo-Rousseau. Okay, and the very last thing I will explain to you in this talk is that there is a striking link between the existence of jet differentials on a given manifold and the fact that it is of general type. And it somehow show a strong link with the Green-Griffith-Lang conjecture. So the precise statement I will give you is that it comes from a theorem, from two theorems, one by Jean-Pierre Demailly and another one by Frédéric Campana and Michael Paun. It tells you that if X is a complex projective manifold, and if you take an ample line bundle on it, then it is equivalent that X is of general type and that it admits differential equations at some order and some degree that vanish along a very ample line bundle. So one direction was proved by Jean-Pierre Demailly in 2011 with using metric methods, and recently I gave an algebraic proof of this direction. And conversely, it is a consequence of a theorem of Campana and Paun that if you have such non-vanishing, then you get that X is of general type. And now what you can do is to use all these differential equations that exist on a manifold of general type and try to form an algebraic locus which will, by the fundamental vanishing theorem, contain all the entire curves. So how can you do that? Take an ample line bundle on X and you construct the following locus. So it's called the Green-Griffith locus. So it's the locus of all the points such that for any order there is a curve through that point, such that for any degree and any differential equation, well, P of f of 0 is equal to 0. Oh, sorry, I have not written here that f of 0 is equal to x in the definition of f. Okay, and now if you recall the fundamental vanishing theorem, well, it implies that all the entire curves you can draw on X will fall inside this locus, which is algebraic and also independent on A. So, as I said, you can reformulate the fundamental vanishing theorem in the following manner. Every entire curve falls inside the Green-Griffith locus. So what you would hope is that on a complex manifold which is of general type, this Green-Griffith locus is different from X, and it will prove the Green-Griffith conjecture for entire curves. But actually, this is not true. There is a work by Diverio and Rousseau, which allows you to find many examples of hyperbolic manifolds such that the Green-Griffith locus is equal to X. So, a simple case where this will hold is the case where X is a product. So, I can give you as an exercise to show that if Y and Z are, say, broadly hyperbolic, then so is X. And in their work, Simone Diverio and R1 Rousseau show that in that case, the Green-Griffith locus is equal to all the manifolds, so the fundamental vanishing theorem does not help you to show that X is hyperbolic. So you have to show it directly, say. And there is also an interesting case where this is true, where you have this equality. It's in the case where X is a quotient of a bounded symmetric domain of rank larger than 2. So, say, a bounded symmetric domain different from the ball. Okay, so I think that's all I wanted to say about complex hyperbolicity. So before finishing this lecture, I will just give you several references concerning the field of complex hyperbolicity. So I have no pretension for exhaustivity, so if you want to learn more about complex hyperbolicity, I strongly advise you to use this bibliography only as a starting point. And then do your own reading if you want to go further in the subject. So concerning the basic facts about complex hyperbolicity, the following three books or articles are very good references, and in particular everything that I have explained in this lecture is included in this first article by Jean-Pierre de Mailly. Concerning orbifolds, if you want to learn more about them, the first article here is a standard reference. And if you are able to read French, the Séminaire Bourbaki, which was given by Benoît Cadorel, is also a very good reference for Campana's theory of orbifolds. It's a very good starting point. About metric methods that apply to variations of Hopf structure, families of varieties, questions of bounded symmetric domains, I can give you only finitely many articles among the very, very many which exist in the subject, and again I have no pretension for exhaustivity. Concerning jet differentials, there are several articles you can read on the problem of constructions of jet differentials, and for example the first two ones I have listed here are based on techniques which were very important for the proof of the algebraic degeneracy of entire curves on hypersurfaces of high degree. And it's the work of Simone Diverio, Joël Mercœur, and also I told you about in the lecture. And you also have then other work on the hyperbolicity of general hypersurfaces, complete intersections, and the work of Rideau and Young. Lionel Darendo will probably told you about in this lecture. And finally, the last work I wanted to mention concerns the results about the Green-Griffith locus I told you about in the last slide of my lecture. And it's this article of Simone Diverio and R1 Rousseau, in which they prove that the Green-Griffith locus is not always equal to the exceptional set. Well, thank you very much. I hope you have learned some things about complex hyperbolicity, and as the organizers have probably told you, I remain at your disposal if you have any questions about the lecture. Thank you very much.